Video title: Advanced New Techniques for Computer Programming. Principles, Frameworks, Algorithms, and Applications. Introduction and Rationale. Computer programming is entering an unprecedented era shaped by transformative emerging technologies, TETs, a convergence of artificial intelligence, AI, quantum mechanics, automation, and intelligent software engineering. Unlike traditional programming, where humans manually define logic, these technologies enable intelligent, self-adaptive systems that generate, optimize, and execute code autonomously. The transformation is driven by global imperatives: exponential data growth, increasing computational complexity, energy efficiency demands, and the limitations of Moore's law. As quantum computing progresses from theory to practice, and AI-augmented programming becomes mainstream, new paradigms are redefining how software is conceived, written, and executed. This video presents a unified framework integrating advanced emerging technologies for both classical and quantum computing, analyzing their concepts, principles, algorithms, tools, and applications. Concepts and evolution of advanced emerging programming. Advanced emerging programming technologies refer to a generation of computational approaches that blend automation, learning, reasoning, and quantum logic within the software development process. They encompass AI-augmented and agentic programming, systems that interpret human intent and autonomously generate and refine code, e.g., GitHub Copilot, Google Gemini Code Assist. Low-code, no-code, and conversational, vibe, coding, platforms enabling natural language-driven development for rapid prototyping. Quantum-aware programming, writing algorithms that leverage qubits, superposition, and entanglement for exponential performance gains. Hybrid quantum classical models, architectures combining quantum subsystems with classical control and analytics. Meta-programming and self-improving systems, code that evolves dynamically through feedback and self-testing. The trajectory from manual to intelligent programming reflects a deeper shift, from descriptive coding to cognitive orchestration, where human creativity collaborates with machine intelligence. Justifications and strategic importance. The adoption of transformative technologies in programming is justified by scientific, industrial, and economic imperatives. 1. Computational scalability. Classical computing struggles with exponential problem spaces, e.g., NP-hard optimization. Quantum algorithms promise exponential acceleration. 2. Automation demand. Global software development faces workforce shortages. AI-augmented coding automates routine programming tasks. 3. Data and AI integration. New AI pipelines require adaptive, self-learning code generation beyond traditional programming limits. 4. Innovation and sovereignty. Countries and industries investing in hybrid classical quantum infrastructures, e.g., Australia, EU, Japan, seek technological sovereignty in computation. 5. Sustainability. Quantum and AI-assisted systems can dramatically reduce energy and resource consumption for large-scale simulations and machine learning. These justifications make advanced emerging programming technologies a strategic frontier for future innovation and competitiveness. Foundational principles of advanced programming: intelligence-driven automation. Programming environments now integrate large language models, reinforcement learning, and knowledge graphs to reason, predict, and adapt code structures in real time. Quantum abstraction. Quantum programming languages like Qiskit, Q-hash, Cirq, and Penny Lane translate physical qubit operations into logical abstractions, allowing classical developers to access quantum capabilities. 4.3 Declarative intent. The programmer specifies what outcome is desired. AI systems determine how to achieve it, aligning logic synthesis with outcome-driven reasoning. Continuous learning and adaptation. Coding agents evolve from past projects, refining their understanding of syntax, style, and optimization, leading to living software ecosystems, ethical and secure development. Emerging frameworks embed privacy-preserving AI, transparency, and explainability into the development pipeline, addressing the accountability challenges of autonomous programming. These principles collectively redefine software engineering as an interactive ecosystem of humans, AI, and quantum systems. Algorithms and computational frameworks. AI-based algorithms for classical programming. Transformer and diffusion models, e.g., Codex, Gemini, generate optimized code blocks using contextual embeddings. Reinforcement learning for code optimization allows autonomous refinement of algorithmic efficiency. Graph neural networks model code dependencies, improving debugging and test generation. Automated theorem provers ensure mathematical soundness and compliance in mission-critical systems. Quantum algorithms, quantum approximate optimization algorithm, QAOA, for combinatorial optimization problems. Variational quantum eigensolver, VQE, for molecular and energy simulations. Quantum machine learning, QML, frameworks integrate neural architectures with quantum kernels. Quantum reinforcement learning agents combine probabilistic decision-making with quantum policy evaluation. Hybrid frameworks. Differentiable quantum programming enables backpropagation between classical neural layers and quantum circuits. Hybrid AI quantum kernels transform classical data into quantum feature spaces for pattern recognition and cryptographic applications. Meta agents for quantum code generation, AI systems that autonomously design, test, and optimize quantum circuits. Advanced techniques and engineering practices. 1. Prompt-oriented development, using natural language prompts to guide code synthesis and refinement. 2. Auto-refactoring pipelines, continuous code evolution based on empirical testing and version control analytics. 3. Noise-aware quantum compilation, algorithms dynamically adapt to qubit errors and connectivity maps. 4. Cross-domain orchestration, integrating heterogeneous processors, CPUs, GPUs, QPUs, within unified workflows. 5. Intelligent debugging agents, autonomous agents that detect, repair, and explain code anomalies. 6. Self-validating systems, programs embedding runtime logic to verify integrity, compliance, and performance. These techniques represent the operational layer, bridging abstract algorithmic design and practical software deployment. Tools and development ecosystems. 1. AI-Augmented programming. Key tools and platforms are GitHub Copilot, Gemini Code Assist, Tab 9, SWE Agent. Functions and features are contextual code prediction, auto-completion, agentic debugging. 2. No-code, low-code platforms. Key tools and platforms are Microsoft Power Apps, Mendix, AppSheet, Bubble. Functions and features are visual programming and rapid prototyping. 3. Quantum development frameworks. Key tools and platforms are IBM Qiskit, Google Circ, Microsoft Q-Hash, Xanadu PennyLane, TensorFlow Quantum. Functions and features are circuit construction, simulation, and hybrid execution. 4. Hybrid orchestration platforms. Key tools and platforms are AWS Bracket, Azure Quantum, NVIDIA CUDA Quantum. Functions and features are classical quantum task coordination and optimization. 5. Collaborative AI agents. Key tools and platforms are LangChain, Autogen, and MetaGPT. Functions and features are multi-agent reasoning, planning, and task execution. The synergy of these tools facilitates collaborative, cross-platform, and intelligent software ecosystems. Software engineering lifecycle in the age of AI and quantum. The I-Quantum software development lifecycle, AI-QSDLC, introduces continuous learning and adaptive verification across stages. 1. Requirement modeling. AI interprets domain-specific needs using semantic and probabilistic models. 2. Design synthesis. Intelligent systems architect modular, scalable solutions with built-in error tolerance. 3. Implementation. Hybrid coding environments orchestrate classical and quantum code blocks seamlessly. 4. Testing and verification. Reinforcement learning agents evaluate reliability, performance, and compliance. 5. Deployment and optimization. Quantum-aware DevOps pipelines balance hardware loads and error mitigation. 6. Evolutionary maintenance. AI-driven analytics monitor usage, refactor code, and adapt to new architectures. This cycle exemplifies self-evolving software, merging agility with intelligence and long-term adaptability. Applications in cross-disciplinary impact science and engineering, quantum AI-enhanced computational fluid dynamics, weather, and fire modeling. Material and chemical discovery through quantum molecular simulations. Healthcare and life sciences, drug discovery and genomics using quantum-assisted pattern recognition. Intelligent prosthetics and neuroadaptive exoskeletons powered by AI agents. Cybersecurity and defense, post-quantum cryptography and AI-enabled anomaly detection. Multi-agent game theoretic systems for autonomous cyber defense. Finance and governance, AI-quantum hybrid systems for risk analysis, fraud detection, and portfolio optimization. Policy modeling and regulatory simulations through agent-based computation. Smart infrastructure and sustainability, real-time energy grid balancing, traffic optimization, and urban analytics. AI-quantum models for water management and climate resilience. These applications illustrate that the fusion of AI and quantum paradigms is not theoretical, it is transformative across industries. Future directions. 1. Development of quantum-native AI agents capable of operating directly within quantum state spaces. 2. Establishment of global quantum programming standards to ensure interoperability and reproducibility. 3. Integration of explainable AI, XAI, frameworks into automated coding ecosystems. 4. Research on bio-inspired and neuromorphic quantum computing, bridging cognition and computation. 5. Expansion of education and reskilling initiatives to prepare a hybrid workforce fluent in both AI and quantum logic. Conclusion. The evolution of transformative emerging technologies for programming signals a fundamental redefinition of computation itself. By merging AI intelligence, quantum mechanics, and autonomous software engineering, programming is evolving from static code creation to adaptive system co-creation. These technologies will shape the next era of science, industry, and education, enabling hybrid computational ecosystems where classical logic, AI cognition, and quantum superposition work in unison to solve humanity's most complex challenges. The future of programming is not merely digital, it is intelligent, quantum, and collaborative.